Greetings. Today we're going to go over 6 problems on specific heat out of the Chapter 10 in Holt's Science Spectrum. It's on page 338 in the textbook if you'd like to follow along. Specific heat is the amount of energy transferred as heat that will raise the temperature 1 kilogram mass of a particular substance by 1 Kelvin, and that's the same as 1 degree C. Note that we're referring to pressure and volume not changing, such as might happen in a gas. Usually these are used on solids and liquids. Now the specific heat equation, E equals mcm delta T. E stands for energy in joules. The mass is in kilograms, and the specific heat is joules for every kilogram of material raised 1 Kelvin. So it's very specific from the definition. This little triangle here is a Greek letter said to be delta, and it's a symbol meaning to change. Delta T, which means the change in temperature, you usually take the end T minus the beginning T, and usually is stated as T2 minus T1. And you can use K or C because they have the same size. In this first problem, we have how much energy is needed to increase temperature, so that's T, temperature, 755 grams of iron from 283 K to 8403 K. So we want to say we have a lump of iron here. Let's say we just have a cube sitting here of just iron. So say it's Fe, an iron. Rising of temperature. So we're adding in some heat. We can just use a candle to represent fire here. That's that being heat. So we're adding heat. And the other thing we can note is that it's 0.755 kilograms, which is the same as 755 grams. And we want to know that it's 283 going up to 403 in Kelvin. Okay, so now we've got to have a little picture of this. Then, so what are we given? 755 grams is equal to 0.755 kilograms. We've just divided by 1,000 by moving the decimal over 1, 2, 3 places. We also know that 403 K minus 283 K, and we come up to that, and we end up with a 0, a 2, and that's 120 K, which also equals 120 degrees C, and this is equal to the change in temperature. Do we need to do any conversions? Well, we've already done. We've done the grams into kilograms already, and that's done. So the only thing we need is the C for iron. Now the C for iron happens to be 449 joules for every kilogram degree K, or degree C. What do we need to find? We're looking for what? Energy. Energy, and we want it in joules. Energy in joules. We have the equation E equals the C times M times delta T. So we've got C, we've got M in the right units now, we've got delta T in the correct units, so we can just plug right in. We don't need to modify. So no, we don't need to modify. Just plug in and solve. So E is equal to the C, which is 449 joules per kilogram times K, and we multiply this by M, and what's the mass? 0.755 kilograms. We just put that over 1 to make it easy multiplication. And delta T, what's the change? 120 degrees C, or K. In this case we have K below, so let's go ahead and change that to a K. So we can cancel the K's, Cancel the kgs, and what are we left with? We have 449 times 0.755 times 120, and it's all about joules, which is the correct unit for energy, so now we're in good shape. So the answer to this is 40,700 joules. Now we have three significant figures in one number, we have three significant figures in another one, and three significant figures in the third one. So that allows us to put an answer with 3 sig figs in the final answer. So 40,700 is a good answer. We can also state this a couple different ways. We can say 40.7 kilojoules just by dividing by 1,000, and therefore specifying that we have exactly 3 digits and no more. And it's easier to say kilojoules than 40,700 joules. It's easier to say 40.7 kilojoules, which says the same thing. In problem 2, how much energy, and so let's put that right down here, how much energy? Find energy, and we want to know this is usually going to be in joules. And we have a refrigerator, and we've got 225 grams of water, 225 grams of water, and so we just can convert that to 0.225 kilograms right away, because we know we do need to convert it, so that's one check off. We have a drop, and it's important to know that we're talking about a drop in temperature or a loss of energy from 35 to 5 degrees. So 35 minus 5 equals 30 degrees C loss of energy. As long as we keep remembering that, it's not a positive increase, it's a decrease in energy. So we know that it's water. What else is given? Okay, it's water. So the C is going to equal 4,186 joules divided by kilograms times K. So our equation that we use is E equals M or Cm delta T. So we have C, we've got mass in grams, we have a change in temperature, but this change is a decrease, so it's the energy that's lost is what we're referring to here. Do we need to modify equation? No, we don't. So let's just plug in and solve. E equals 4186 joules per kilogram K times, and the kilograms is 0.225 kilograms divided by 1 times change in temperature, and we're talking about 30 K, since this is the same right up here as a 30 K change equals the delta T. They're the same. So put that over 1, and so what do you end up with? Canceling K, canceling Kg, and then simply 4186 times 0.225 times 30, and what are we left with? Joules. And is that a unit of energy? Yes, it is, so we're in good shape. We don't need to make any modifications or go back for corrections. We know we're in the right direction. So this comes out to be 28,215 joules from the calculator. Too many digits. So what are we allowed? We've got 2 digits in one measure, 3 digits in another measure, and 4 digits in another measure. So that allows us to use only 2 sig figs in our answer. So we've got to reduce this down from 28,000. We can just say 28,000 joules and rounding it. Another possibility would be 28 kilojoules, which is simpler to say. And that would be a nice final answer. Problem 3 gives us that 140 kilograms park bench made of iron. It really doesn't doesn't matter if it's a park bench for this problem or not. It's made of iron. That's what really matters. And it's in the sun. It could be a heat lamp, so that's not really important. So sometimes we want to just eliminate information that we don't really need. So 144 kilograms of iron. It's warming up, so we know that is added. So we can say added. So we're adding in heat. So just make a note. Instead of the sun, just say added heat. And its temperature increases from 25 to 35. So now we have a 10 degrees C equal to a 10 K, and this is going to be our change in temperature. How many kilojoules? They're asking us not for joules, but kilojoules of energy does the bench actually absorb? Okay, so here we just might have a little bench that's sitting down here. Put some legs on this thing. And the sun's shining on it up here. And so we're adding in heat. So sometimes you really want to notice that we have what it is and how to deal with it. And what do we have? And it's iron. So one of the things that we know immediately, what is the C? C equals 449 joules for every kilogram K, or degrees C. We also know that we have delta T is now equal to 10 degrees C equals 10 K. And we want to find the kilojoules of energy. Normally energy is in joules, but we need to make some conversion here to make sure that it's kilojoules in the end. So the equation, E equals Cm delta T. We have C. Do we have M? Yes, we do. It's 144 kilograms. So let's just add up here. So mass equals 144 kilograms. And do we need to convert anything? No. We're in all pretty good shape right now. But at the end, we'll do something. Okay, so do we need to modify equation? No. So let's go right ahead and plug in and solve. E equals, C, 449 joules for every kilogram K times, and our mass is 144 kilograms times, and we have a change in temperature of 10 K. And so we put this together, 449 times 144 times 10, and we can of course eliminate the kg, eliminate the K, and we just end up with joules of energy. So this number comes out to be 646,560 joules in the calculator. Again, we only have two significant digits in our temperature, so we're only allowed 2 in our answer. So we can round, and we end up with 650,000 joules. Well, since that is the same as 650 kilojoules, we just divide by 1,000 and use the word kilo instead of joules, and that would be our final answer. In problem 4, we now have aluminum, Al, baking sheet with a mass of 225 grams. So one of the things we think of, 0.225 kilograms. Absorbs 2.4 times 10 to the 4th joules. Okay, joules is pretty nice, so at least that fits into the equation. And it's from an oven. Okay, if its temperature has initially 25 degrees C, what will its new temperature be? Okay, so we know what its T1 is, and what was new temperature? That's going to be T2. So we've got this baking sheet, and it's got some cookies on it, and we have some sort of heat element. I'll represent that again by a candle. That's a universal symbol. And we know that it is aluminum now, which is a different material. So we go ahead and look up aluminum, and we find the C of aluminum is 897 joules for every kilogram of material raised 1 Kelvin or degree C. We have a mass is going to equal 0.225 grams, kilograms. I have to remember that. We bring that all the way down from up here. And what do we want to find? We want to find the second temperature. Okay, so we've got to do some calculations. First off, we know that E equals Cm delta T, so we need to convert that over. Can we divide both sides by C and M? Yes, and then we can cancel, and we now have a solution for delta T. So delta T is going to be equal to E divided by C times M. Let's go ahead. Now we've modified the equation just fine, but we will still need to convert from delta T. We'll need to go to and find T2 in the end here. So let's just keep that in mind. So plug in. So delta T is equal to E, which is now 2.4 times 10 to the 4th joules, divided by C, which is 897 joules for every kilogram K, and this is times the mass, which is 0.225 kilograms over 1. And this line extends all the way across. Okay, so one thing we know, well, kilograms can cancel. That's a good thing. The joules can cancel. That's a good thing. And we also know on this side that 1 over K is also equal to K. So we know we're going to end up with K as the final answer. So we can take the K off out of here and just put it over at the tail end and know that we're in Kelvin, and that's the change in temperature. So now we can do this. Okay, in your calculator, well, some folks can't put in the times 10 to the 4th. So we could also just write that as 2400 and then another one, because we have 1, 2, 3, 4 places we've moved things. Okay, so that many joules, or it used to be joules, and now we divide by 897 times 0.225, and so this is all in K. This we can put in a calculator, and what do we end up with? 118.91490 Kelvin according to the calculator. Okay, but let's go back. How many sig figs do we have? We've got 2 sig figs, 2.4, 3 sig figs, 0.225, 3 sig figs, 897. Therefore, we're only allowed 2 sig figs in our answer. So, okay, so let's round this off. Equals 120 K, which is the same as 120 degrees C as far as change in temperature. Remember, this is change in temperature. So finally, we say, okay, what do we have at the start? 25. So 25 degrees C, and have we added or removed heat? We've added. So we add the 120 degrees C, and we end up with 145 degrees C as our final temperature in our answer, 145 degrees C. In question 5, what mass of water is required to absorb, keyword here, absorb, 4.7 times 10 to the 5th, I should have written that as a 5th up here, joules of energy from a car engine while the temperature increases from 298 K to 355 K. So first off, we have to know this is a water-cooled engine, and the water is going to absorb the energy from the engine. So the engine to the water. So we've got a combustion engine here. Let's say an engine block in here, and it might have a little some piston heads in here, and it's got a drivetrain that goes through it, an axle. But what we also have here is there's got to be a radiator in the front here, and they're connected by 2 tubes. Water's coming in and out and circulating, and we have a little top up here, and this is called a radiator. And the circulation of the radiator, and it's got H2O in it. So now we have energy being generated from here, and the flow of energy is in this way, and then the cooling is going back in, cooler water to help keep the engine cold. So we're given it's water, and so what's the heat capacity of water? Is 4186 joules for every kilogram K. We also know that the temperature rose, so 355 K, this is T2, minus 298 K, this is T1, and so we subtract the two, and we end up with 57 K as far as a change in temperature. That's change in T. So we've got E up here, that's energy in joules. We've got C, and we've got change in temperature, so those are fine. And what is it we want to find? We want to find mass. We want to find this usually in kilograms. So the equation E equals Cm delta T. In this case we want to solve for m here. So we want to divide by C delta T and divide energy by C delta T. And we end up with, cancel those out, and we end up with mass here on the side. So mass is equal to the energy divided by specific heat times the change in temperature. So now we can plug in and solve. So M is equal to the energy, and we have 4.7 times 10 to the 5th joules divided by C, which is now 4186 joules for every kilogram K. And then we multiply this by the delta T, which is up here is at 57K. 57K. Extend this line over, make sure we can see it. And now how can we cancel things out, make things simpler? Well, the K goes away, the joules get canceled out, and again, just as a note, 1 over kg is the same as kg, because 1 divided by 1 over kg is kg. So let's go 4, 7, 1, 2, 3, 4. We know we've moved over 1, 2, 3, 4, 5 places here. Okay, good. Then we divide that number by 4186 times 57, and that's equal to, and of course we're going to end up here in kilograms because we have the kilograms left, is 1.9689807 kilograms on the calculator. This is from the calculator. Okay, so we don't have all these zeros, so we have 2 sig figs here, 2 sig figs in this, and 4 here. So that gives us a total of 2 sig figs allowed here. Everything else kind of gets eliminated, so let's just cut that stuff off, and we'll just call this 2.0 kilograms. So that's going to be our final answer. In problem 6, we have vanadium bolt, which is a type of mineral, and we have 1,124 joules of energy as its temperature drops 25 K. So remember, it's important that it's dropping here when we deal with the temperatures. It has a bolt mass of 93 grams. What is its specific heat? So in this case, we've actually put this bolt into some sort of a refrigeration unit. So let's draw a refrigerator around this, and this is refrig in here. So it's in this box, this refrigerator, and we're cooling it down for some reason. So what's given? C of vanadium is going to be unknown, so actually we should put that down here. See if that's what we're looking for. And we're going to want it to know it in joules for every kilogram K. Oh, we have grams up here, so that's one conversion we need to do. So just make a note in here. we have to go grams to kilograms. So we have a drop of 25, so 25K is going to be equal to a drop. That's a change in temperature, so that one's taken care of. We have a mass equals 0.093 kilograms, because we're able to convert over by dividing by 1,000 to get the kilograms. And the equation we're using is E equals cm delta T, all multiplied. And we're looking for C, so we have to divide by m times delta T, divide by m delta T, and then the m's cancel, delta t's cancel, equal to C. And so now we have modified the equation adequately, and we go down to the plug-in now. So C is equal to the energy, 1124 joules, divided by, and the kilograms is from up here, and we have, remember, it's 2 sig figs in here, just as a note, so 2 sig figs up there. So 0.093 kilograms times, and then we have a temperature change of 25K here, so 25K, and we're going to end up in units of what? Joules per kilogram K, which is the correct units, so we're now on the right track. So now we just have to divide 1,124 by 0.0093 times 25, and that gives us 483.44 on the calculator, joules per kilogram K. So we need to round to just 2 digits, since that's all we have in any of the original measures. So this rounds to 480 joules per kilogram K, and this is for vanadium.